Okay, so what we're going to be doing is this is a little video to go through the Year 11 November assessment. And so what I'm going to do is work through it, show you the answers, show you what the mark schemes are. So if there's any questions you needed to go back through, this should hopefully help. So obviously, unlike previous exams, you get a lot more equations, which is lovely news. And we go straight on into question 1. So this question is about the motion of a ball. The ball is at rest on a trapdoor. Complete the diagram to show the forces acting on the ball. Label the forces. So the key thing that is really important about this, is this sentence here. Okay, it's at rest. If things are at rest, that means the forces on them are balanced. It's not moving sideways, so there is no air resistance or friction, nothing going on. So really just dealing with a force downwards, okay, which is, I'm going to use a thinner pen, which is exciting, which is weight, okay, and you must use the term weight. You cannot use the term gravity. Weight is the force due to gravity, so it must be weight. And then what do you have upwards? Well, you've got another force which is upwards, probably that bit thinner as well. And doesn't want me to do that, so excellent. Fine on that. And now this force, it has a couple of different names. It's coming from the fact that the ball is pushing into the trapdoor. It's sometimes called a reaction force or a contact force, because it's in contact with the trapdoor. It's not upthrust, because that's to do with water. It's not drag, it's not friction, it's not air resistance, none of those forces are acting, just these two, one up, one down. So 1 mark is for this top one, 1 mark is for the second one. The third mark is for these arrows being about the same size, just by eye that they are the same size. Okay, so B, trapdoor swings open, the ball falls to the ground. The ball does not bounce when it hits the ground. Show the final speed of the instant before it hits the ground is about 5 meters per second. So the solution to this one, we're using the equation that you get given, which is v squared equals u squared plus 2 times acceleration times the distance moved, which is the equation that is here, this one here. That's the equation you're using. Final speed squared equals initial speed squared plus 2 times acceleration times distance moved. Because it's at rest, u is 0, okay, and we've got 2 times acceleration due to gravity, because gravity is things making a move, which is 10, times the distance, which is 1.3. So that equals 26. And so V is equal to the square root of 26, which comes out as being about 5.1 meters per second. What are the marks for? There isn't a mark for selecting this equation. There is a mark for substituting in, so putting these numbers in, you get a mark for that. And then a mark for basically the rearrangement of realizing you've got to do the square root, and then a mark for the answer. So that's what you get there. See, the graph changes how the distance travelled by the ball changes with time. Determine the time taken for the ball to hit the ground. Well, it's going to be at this point here, which is 0.51 seconds. Calculate the average speed of the ball after 0.4 seconds. Now, this is a poorly worded question, actually. So we are allowing a few different things. It's interpreting the intention of the question as written is, after 0.4 seconds have elapsed, what was the average speed of the ball, which is simply 0.8 divided by 0.4, which is therefore, speed is equal to 0.8 over 0.4. Should just equal 2 meters per second. That's the answer that's in the mark scheme that's expecting, but it's perfectly reasonable to interpret that after 0.4 seconds should actually be from here to here, because this is after 0.4 seconds, which is 0.5, because that's 1.3, there. So that is 1.3. So you actually get 0.5 over, in this case, 0.2, which gives you 2.5 meters per second. We accept either because actually it's a reasonable thing to write either answer. It's a poor phrasing of the question. So explain how the graph shows that the ball accelerates when it falls. So these are the key points that you need to be talking about. So the first thing is what does this graph show? It's a distance time graph. So in a distance time graph, the gradient is the speed. Okay, so the gradient is the speed. The gradient is increasing, which therefore means that the speed is increasing. Okay. Now there are a few different ways to talk about it. I've seen people who write down that who did some calculation of the graph of doing an average speed here and here. So the speed is, so you can show from the graph the speed is increasing. You don't necessarily need to. What's important is that you can't just sit there and saying, so it's accelerating, because you're already given the word acceleration. Okay, so you need to sort of make an explicit link between acceleration being an increase in speed. Commonly with this, the second 2 marks were easy to get, and the first one is actually very rarely with people saying that the gradient is what the gradient is actually representing. People tended to say, oh, the gradient's getting steeper, so it's accelerating. And what was the gradient representing? Now with this question, something to highlight is that this is a question that didn't come from a full exam. It came from a sample assessment material when they changed the specifications. So one of the reasons the mark scheme in these 2 bits is a little bit narrow is because normally what happens is thousands of children submit answers, and they are considered when they devise a mark scheme. So because this was never sat as an actual exam question, there would normally, I would expect there to be more things that would be allowed, but we obviously don't see them because this wasn't a full exam question. Okay, so that's what we've got there. Question 2. Use the graph to determine the reaction time of the driver. Zoom in. Okay, so we've got a line that's just about here. So the reaction time of the driver is when this thing starts to decelerate. So that's when we realise that we've stopped. So the reaction time of the driver is 0.9 seconds. What is the stopping distance of this car? The stopping distance is the thinking distance, which is this bit here, and the braking distance. We have a rectangle, we have a triangle. So we've got to, so the 4 marks are for representing. 1 mark is for recognising that it's that we're after the area under this shape. So there is 1 mark for some idea that you're looking to try and calculate the area. The second mark is for calculating either area. So this is 15 times 0.9, which is, so the thinking distance. So red. So this area here is 15 times 0.9, which is 13.5. And the area of this one, because it's a triangle, is a half times the base, which is 3.1, because we're going from this time here, which is 0.9 seconds, to 4. And the height is again 15, which is 23.25. And so the total stopping distance is these 2 added up. So you get about 13.5 plus 23.5. Oops, that should be, really should clean that up. 23.25. So we get 20, so we add these 2 together and we get 36.75. which is basically 37 meters. Okay, so there's a mark for if it's clear that you're trying to work out an area, it's a mark. If you calculate either the rectangle or braking distance, you get a mark. So adding the values together, showing that you're adding two values together, gets you a third mark. Final answer, fourth mark. Calculate the acceleration of the car when the car is braking. Who else has done this? So acceleration is the gradient, okay, and so we've got acceleration is equal to the change in speed over the time, so which is v minus u, so okay, and what's our final initial speed? Sorry, our final speed is 0. Our initial speed is 15. The time, again, it's 3.1. It's not 4. We were not accelerating here. We're only accelerating once we pass the 0.9. So over 3.1, and that gives minus 4.8 meters per second squared. So one of the key things here, one of the marks is for recognizing this is a negative. Okay, this is a negative number because you're decelerating. So that's really acceleration of the car when it's braking, you know, and you're slowing down. So the negative is important to show that you are slowing down. Right, the speed of the car affects the thinking distance and the braking distance. Discuss other factors that affect the thinking distance and the braking distance. So this is a sort of recall, but you've got to be quite clear about which one, what you're talking about. First off, the speed of the car, they've said it already affects it. So you can't say speed again, okay? Can't say speed. So thinking distance, you've got tiredness, age, drugs or alcohol. And this is a really nice one because they do allow you to talk about distractions. Sometimes they don't allow that one, but in this mark scheme they do, so that's allowed. And then we've got our braking distance. Well, that's going to be affected by brakes, the road surface, whether it's slippery or wet, road, so it's the road condition, the road slope, because it's going up or down is going to be different, and then you've got the tyres. The final one is the mass. Okay, so those are the things that affect the braking distance. So any two from your top, from the blue lot, any two from the red lot, are what can give you the marks for that. Okay. Ooh, whoops. Don't want to do that. Okay, so, gosh. Aha, we've got a ball. We've got a ball is dropped from a very large height. The graph shows how the velocity of the ball changes until just before it hits the ground. Explain why the velocity of the ball changes in this way. Refer to ideas about forces in your answer. So, so we've got to talk about forces. Okay, so the two forces that we're going to have to talk about are our weight, and we're going to talk about air resistance. Okay, they're the two forces that we have to make reference to in order to make sure that we get marks. So if we talk through what we want, we will have the so we've got the weight. The weight is acting downwards initially, well, all the time. Okay, so therefore, so the ball will accelerate. Okay. This, you know, as the ball will get faster, we will then get drag will upwards gets larger with increasing speed. Okay. So if initially we're dominated by weight, but as we fall and we get faster and faster and faster, eventually what's going to happen is that weight and air resistance are going to be balanced. So Sorry, I've mixed up. I've said air resistance and I keep air resistance or drag, same thing. Apologies. So eventually, drag equals weight. So the overall force is 0. So therefore, we have a constant velocity, or if you wanted to say we've reached terminal velocity, or has 0 acceleration. Other things you can say that are equivalent, anything you want to say that's equivalent to that. 1, 2, 3, 4. So these are actually increased from this. We've got 7 points here. So we've got weight, acceleration. The drag upwards is 1 point, and then gets larger with increasing speed or as it accelerates. That's actually 2 points in that one there. So eventually drag equals weight. So overall force is 0. So you have a constant velocity or 0 acceleration, or you've reached terminal velocity, and that's the point of that one. Right. Excellent. Question 4. Right. Okay. Which of these is a scalar quantity? Weight is a vector. Its force, momentum is a vector. Velocity is a vector. So the only scalar one is mass, which is B. Which of these is a vector quantity? Acceleration. It's the only vector quantity. We met that earlier because it was a negative, so we have to have. The diagram shows the forces acting on 4 balls falling in the air, which shows a ball that's decelerating as it falls. So they're all going downwards. Okay, and they're slowing down. So what we need is an upwards force that's bigger than a downwards force. The only one here is this one here, so it's B. Excellent, that was nice and easy. Oh, the squirrel question. Oh, what a lovely question. A flying squirrel is an animal that can climb through the air. Here's a picture of a flying squirrel by Robert Savannah. Well done him. Got the mass is climbing. We're calculating the GPE gained by the squirrel during the climb. Okay, so we've got GPE equals mass times gravity times height. There's a selection mark here because you selected the right one, so we're going to substitute our things in. So we've got a mass of 0.19 times gravity, which is 10, times height, which is 17, and then we get, so that gives us 32. So 1 mark for selecting our equation, 1 mark for putting numbers in, 1 mark for 32. State the amount of work done against the force of gravity by the squirrel during this climb. It's a 1 mark question because if you gain this much energy, you've done that much work. The answer is simply 32 again. Okay. The flying squirrel glides from P to Q with a constant velocity of 13 meters per second. Add labelled arrows to the diagram to show the directions of the forces of weight and drag acting on the squirrel. So, got weight, which is going to be acting downwards. Where does drag act? Because it's going in this direction, drag always is against the way you're going. So that's drag. No. Calculate the kinetic energy of the squirrel as it glides. So this time selecting the equation k equals a half times m times v squared. So we've got a half times 0.19 times 13. There's our number. 13 squared. 13 squared is 169, which is something that was drilled into me in primary school. So what we get here is an answer of 16. The velocity of the squirrel decreases to 0 when it reaches the second tree because if it's decreased to 0, there must be an unbalanced force. It's just A. And then we're on to the final question, I think. Yes, we are. Okay, so the manometer, the device used for measuring differences in pressure. Right. This is an interesting sort of thing. So you've got an open tube here and a closed tube here. The greater air pressure in your room, the more the force exerts on this liquid to push it around. So you end up, so the height of this thing is what tells you what the air pressure is. Anyway, difference in pressure can be calculated using this formula. Oh, difference in pressure is height times density times 10. Fantastic. Oh, good. It's even there in the question. Density of liquids is there. difference in height is 3.8 centimeters. Aha! There is our trap. 3.8 centimeters equals 0.038 meters. Calculate the difference in pressure between the atmosphere and the trapped gas. So what we've got there, so there's going to be 1 mark there for a conversion. So we get the change in pressure is equal to height, which is 0.038 times density, which is 13,000, which is 1.02 times the 4 times 10. And that comes out as being 4,900. Okay, about 4,940, I think it comes out as being. And there we go. And that's the last of the questions. So hopefully that has helped. If you were asking about where do they get marks from any of these places, there you go.